I went to the homecoming dance. Anyone go to the homecoming dance for BHS? I know, West, your homecoming dance is coming up on the 20th because homecoming's coming up a couple weeks for you guys. That's exciting. Very different the way the two high schools did it. BHS had the homecoming game Friday night. They won. They all went home. Yay, we won. Went home. Then Saturday, they decided to have the homecoming dance on Saturday night. So then it's not really homecoming dance because it didn't feel like homecoming at all. It's prom practice because all the girls are all dressed up and so I mean it was nice, it was cute. It's just very different than the way West is doing it. And the West is doing, go have the football game, hopefully you win, yay, and then you go straight from the stadium to the dance. That's a very different feeling. I mean, a lot of cheerleaders, a lot of times they'll go in their cheerleading outfits. Everyone's straight in your whole thing. And it is a homecoming feel because you just came from the game. You're all pumped up and excited from the game. And you step right into the dance and everybody's at it. The BHS homecoming, everyone comes in, they're kind of subdued and everyone's kind of, and it takes a while to build up that excitement because they just came from dinner or home or wherever they were before the dance. So it's a very different feel. Whichever one you prefer. I mean, there's not a wrong way and a right way, but it's just very different approaches to homecoming. So I don't know. I kind of like going straight from the game to the dance while you're all pumped up and excited from the game. But you can do it either way. And our two high schools are doing it different ways. So interesting. I did learn how to dance with your generation, though, because every dance, there's like 100, 150 people out there going, jumping, just like this. It's a fast dance. It's maybe some hip hop. Maybe it's one of those slow dances, where slow dance. We're out here like this in a slow dance. And it kind of cracked me up because it's like normally that's when you got your date. Maybe you do a little slow dance like this, but no, slow dance. So it was just kind of funny. Yeah, but it was for every single dance. It's like every single song. Didn't matter the style of music, the speed of the music. It kind of cracked me up. But I was there handing out water bottles and snacks for the 3 hours because my wife is in the science department, and the science department handled the homecoming dance. So since she was assigned, I went with her and got to check out the homecoming dance. So it was an experience. So we're missing like 5 people still here. I figure if I killed a little time, people would show up. Well, we got to get going. We got a lot to cover today, but interesting to see. Do I have it recording? I do have recording because we'll need to edit this and post it online. All right, let's pull up our screen. Let's see, fifth hour. There's fifth hour right there. Okay. Let's go to our grade screen. There we go. October 8th is this Sunday. So this is our lessons. We're doing 2.06 and 2.07. Complex numbers and operations on complex numbers. And you can see next week we've got one more lesson, polynomial operations, and we'll have our practice test. So practice test next week, and then our unit test to be the week after that. So that'll be the week after our fall break that's coming up. Those are our next 3 weeks mapped out, and then we'll get into module 3, which I've already opened up. If anybody's wanting to work ahead, I've got it opened up basically all the way to Thanksgiving. Pretty close there, all the way to Thanksgiving. So I'll take a look at that. All right, 2.06, 2.07. Let's go to our activities and look at complex numbers today. Complex numbers lesson right here. Eventually. Maybe. Oh, yeah, there it is. Okay, so we're going to learn about a new type of number. This may be new to you. Maybe you've seen it before, but we're going to talk about the complex number. But in order for you to understand complex numbers, you have to understand imaginary numbers, which may or may not be new to you. But we're going to learn about imaginary numbers and what causes the need for that and what types of parts are necessary for a complex number. So first, let's review on what is a real number. If we're going to talk about imaginary numbers, you need to understand real numbers, right? Because if you don't understand real numbers, then how are you going to understand imaginary numbers? Real numbers are the numbers we've used in all of our math classes since you started school when you were a wee little thing. So there's different classifications: natural numbers, whole numbers, integers, rational numbers, and irrational numbers. Those are all part of the real number system. Let's look at that with a illustration down here. Here's a little, I don't think it makes it much bigger, but I can put it in the center of the screen anyway. Oh no, that's just the words, the text version. So here's a picture of the real number system. So let's start in the middle and look at the natural numbers. These are the counting numbers. These are some of the first numbers that human beings ever discovered. 1, 2, 3, 4. It's all the integers that are the numbers that we use when we count things, because that was from earliest man. What they figured out is they needed to count. If I'm a shepherd, I need to know how many sheep I have to make sure I have all my sheep, right? They'll learn to count. 1, 2, 3, 4. At the time, they didn't understand zero because I couldn't count 0 sheep. I just didn't have my sheep yet. But at some point, it became necessary to look at 0. So that's part of our whole number system. Natural numbers are just starting at 1. Whole numbers adds 0 in there. So that's all the whole numbers. Then we get to the group of integers. And that includes everything that's in the whole numbers group, plus the negative integers. -3, -2, -1, 0, 1, 2, 3. Those are all integers. Then all of those numbers are also in the group of rational numbers, but rational numbers add like -3/4 or 1/6, -2, 0, 1. See, they're all in there, but the fractions are added in that, the rational numbers. And then outside of this group is the irrational numbers. They're all part of the real numbers, but there's rational numbers and irrational numbers. Irrational numbers are like the square root of 2 or pi or 3.1242858 that doesn't repeat and goes on forever. Anything that can't be represented by a fraction like that is the irrational numbers. So that's the real number system. Now we're going to be talking about the imaginary number system, which would be totally separately. See over here, imagine it's right there on the right. Okay, I'm just making a joke there. The imaginary numbers is what we're going to look at this time. So imaginary numbers. What pair of identical factors, identical, that means the same thing twice, right, would produce -1 when multiplied together? How could we multiply something times itself and end up with -1? Well, 1 times 1, that wouldn't work, right? Because that's a positive 1, not a -1. If we went with -1 times -1, that also will not produce -1 because it makes it a positive, because a negative times a negative is a positive. Now, 1 times -1 does equal -1, but those are not identical factors. That's taking 2 different numbers and multiplying. So to solve this problem, the concept of the imaginary number I was invented. I is a number in mathematics, and it equals the square root of -1. That's what I equals. So it's defined as I equals the square root of -1. So with this definition now, we can use imaginary numbers and have negative values when we square something, because we can square the square root of -1. Let's look more at the history of the imaginary number. What kind of came in to play to get us here to where we're at now? See, up until this point in your math education, you've been working with numbers in the real number system, but we're jumping outside of the real number system and look at numbers that are not included there. So these are called complex numbers. That's what this lesson's about, complex numbers. And complex numbers do not exist in the real number system, although they do have a real part. So what makes these numbers special is the existence of the imaginary numbers. So you're thinking, why do I need to know about imaginary numbers if they don't even exist? Well, they exist. The term imaginary is really an unfortunate title, because then they exist, just not in the real number system. So why do you need to know about numbers at all? Well, throughout history, there have been times where a mathematical construct was invented before it had a purpose. They didn't even know why it was invented. They didn't know how to use it, but they discovered it was there. Like we knew the concept of 1 before we knew the concept of 0. At some point, there was figured out, okay, well, 0 exists. I have 0 sheep, but how is that mathematically relevant? And later on, we found uses that 0 was necessary to use that. But there was no need for the concept of 0 originally. When fractions were defined, they were thought of as useless. Why would I ever need a fraction? Why 1 over 2? Or now we use fractions all the time. If you have recipes, you'll have half a cup of flour or something. Counting money, everything you buy is not $1, $2, $3. It's maybe $1.25, maybe $2.50. There's a fraction in there. It may be 63 100ths, maybe $3.63. So 3 and 63 100ths. We use fractions all the time. Telling time. This class doesn't start at 9 o'clock. It starts at 8:55. It's a fraction of another hour, 55 minutes. So the concept of imaginary numbers has a similar history. So if we solved x squared minus 9, that's something you're familiar with, right? We'd move the 9 to the other side to where you've got x squared equals 9. And then since we're trying to get x and it's squared, we would do the opposite effect, which is taking the square root of x squared and the square root of 9. And that would give us an answer of plus or minus 3. Because 3 times 3 is 9, and negative 3 times negative 3 is 9. So that would give us what x equals. But what about if we had x squared plus 1 equals 0? Well, we could do the same process. Negative 1 to both sides. X squared equals negative 1. Then we take the square root. And so x would equal the square root of negative 1. And that's where mathematicians ran into difficulty. Wait a minute. Square root of negative 1. So all of the radicands that they and you had been working up to that point were positive radicands. The number underneath the radicand, under the radical, under the square root, or the cube root, or the fourth root, or whatever root, that's the radicand. They'd all been positive. So to overcome this obstacle, they created the number I, which was declared to be the square root of negative 1. So it says how to simplify an imaginary number. This is important. We need to know how to simplify imaginary numbers. There's a lot of problems about this on the test and on the lessons. So let's simplify the square root of negative 4. So the square root of negative 4, if we want to simplify that, we need to break it out into its two parts. The square root of negative 1 times the square root of 4. That's the same thing as the square root of negative 4. But there's an important difference about changing that, because the square root of 4, that's a number. We can take that. That's a real number. That's not an imaginary number. So the square root of negative 1 we know is defined as I. So we have I square roots of 4. But the square root of 4 is 2. So it simplifies to 2i. We don't do the plus or minus 2. We're just doing 2i just to simplify it. So the square root of negative 4 simplifies to 2i. That's the same thing as the square root of negative 4. All right. But isn't I a variable? Well, not when it's in italics. If you write I in italics, that is the mathematical number I, which equals the square root of negative 1. Okay, here's a video simplifying the square root of negative 8. I'm not going to go through all of that on the video, but let's write it down on paper and take a look at it to kind of go through the process, because this is an important thing you need to get out of this lesson, is how to simplify radicals. Okay, so the square root of negative 8. In order to simplify that, we need to rewrite it. So that's the same thing as the square root of negative 1 times the square root of 8. Right? These are equal to each other. Okay, focus. You're not focusing. There we go. But we can rewrite the square root of 8. If we're going to simplify it, let's see, square root of negative 1 times the square root of 4 times the square root of 2. That's the same thing as the original, because we know the square root of 4 times the square root of 2 is the same as the square root of 8. That's 4 times 2 is 8. 4 times 2 is 8. So this is the same thing as this, which is the same thing as this. It's just written in a different form. But now we can simplify this. The square root of 4 is 2. The square root of negative 1 is I, and the square root of negative 2 cannot be simplified any further. So this is the simplified square root of negative 8. 2i square roots of 2. So we need to understand how to simplify, because we're going to need to do that a bit. So if you want to watch this video, 1 minute, 3 seconds, it goes through what I just went through on paper. How about simplifying the square root of negative 45? All right, let's do that one then. Works very much the same way. Square root of negative 45. So if we rewrite that, that's the square root of negative 1 times the square root of 45. Same thing. But we can write the square root of 45. When you rewrite this and break it apart, there's more than one way to get 45. That's 15 times 3. It's 45 times 1. It's 9 times 5. You're looking for the combination that will be able to take the square root of. We can't take the square root of 3 or the square root of 15, but we can take the square root of 9. So let's rewrite that as square root of negative 1 times the square root of 9 times the square root of 5. So we'll do 9 times 5 equals 45, because 9, square root of 9 is 3, square root of negative 1 is I, and this is as simplified as it gets. So the square root of negative 45 is 3i square roots of 5. These are all equal to each other. It's just rewritten in a different form. So these are the steps you would go through. Break out the negative 1, then take the 45 and break it out into factors that you would be able to simplify, because the square root of 9 we could take as a 3. All right, and it'll go through these steps here too. You can look and see. So breaking out the I part of it, the square root of negative 1 and 45. And then they take the 45, make it 9 and 5, and eventually end up with the 3i. All right, let's look at page 2 here. Okay, so let's see what happens to an imaginary power I when it's raised to a power. This is very, very important to understand too in simplifying, because a lot of times we're going to be dealing with I to a higher power than just by itself. So I'm going to do this on paper as well. So let's draw a line across here, and let's talk about, well, first I is just the square root of negative 1, right? So what's I squared? Well, I squared would be the square root of negative 1 squared, because that's what I is. So the square root of negative 1 squared means it's the square root of negative 1 times the square root of negative 1, because when you square something, you're multiplying it by itself. So since we have two things, we can go the other direction. The square root of 4 times the square root of 2 is the square root of 8. So let's multiply these go. So this is the same thing as the square root of 1. Now let's not do it that way. I changed my mind. Let's talk about the square root. When we have the same number under here, if we have, I'm going to step up here. If we have the square root of 3 times the square root of 3, going that way, that's the square root of 9. But what is the square root of 9? It's 3. When you square a square root, it basically just canceled out the square root. You cancel that out, and it would just equal. I did not erase it very well, but it's not going to. That would equal negative 1. The square root of negative 1 times the square root of negative 1 is negative 1. Because these cancel each other out. They're opposite operations. The square root and the square cancel each other out, and you just end up with what's underneath there. So I squared equals negative 1. I is the square root of negative 1. So what about I to the third power? Well, that means it's I times I times I. right? And I times I is I squared, right? Because that's taking something times itself. And we know I squared equals -1. So this is -1 I, which is the same thing as saying negative I. So I to the third is just negative I, which we know would be negative square root of -1. I to the fourth. That's I times I times I times I. Well, that means you got I times I and I times I. You got I squared and I squared. Well, that's -1. So that's -1 times -1. -1 times -1 is 1. That's a real number. It's the number 1. This is a real number, -1. So when you start squaring and higher exponents than that, sometimes it becomes a real number. I is just square root of -1. I squared is -1. I the third is negative I, which is negative square root of -1. And I to the fourth is 1. What about I to the fifth? How about I to the 13th? How about I to the 26th power? How about I to the 52nd power? Well, there's a really cool trick to that. We don't have to continue doing this. If I want to find out what I to the 23rd power is, what is I to the third power? Well, I don't want to have to do this. I don't want to have to keep going down I times I times I times I times I all the way to 23. I don't have to do that and figuring all this out. But we don't have to, because if we look at this, let's look at I to the fifth. We'll look at a few of these and we'll start figuring out there's a pattern here. So I to the fifth. So I to the fifth is basically, if you remember our rules of exponents, remember exponents, if we have x to the a power plus x to the b power, that's the same as x to the a plus b. We can go backwards. So I to the fourth is the same thing as I to the fifth is the same as I to the fourth times I to the first. That's using this power. You just add them together. Am I doing that right? Plus. No, it's not plus, it's times. I'm doing something wrong there. Nope. Sorry. It's a x to the a power times x to the b power. You just add those together. That's what I was doing. It's not adding down there. If we have x to the second times x to the third, that means x to the 2 times 2 plus 3 is fifth. Yeah, let me write that as a example that we can work with. X squared times x to the third is x to the fifth, because this is x times x, and this is times 3 more x's. So you got 5 x's being multiplied to each other. So if I to the fifth, right there, could be, I could say I to the third times I squared, but I'm doing this on purpose. I to the fourth times I. Because what's I to the fourth? 1. So that means I to the fifth is just I, because it's 1 times I. Oh, so it equals just this. How about I to the sixth? Well, that would be I to the fourth times I squared. Well, this is 1, so it just equals I squared. And we can continue that. I to the seventh is I to the fourth times I to the third. So it just equals I to the third. I to the eighth equals I to the fourth times I to the fourth. I to the fourth times I to the fourth, 1 times 1. So it's the same as I to the fourth. It's just 1. And this equals -1, right? So what we see is I to the first, second, third, fourth repeats here. I to the first, second, third, fourth. And that will continue if we went on I to the 9th, I to the 10th, I to the 11th, I to the 12th. This is just going to equal I. This is going to equal I squared. This is going to equal I to the third. This is going to equal I to the fourth. It keeps looping around. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Every time you raise the exponents, because I to the 9th would be I to the 4th times I to the 4th times I. And since I to the 4th is just 1, it's 1 times 1 times I. So if we want to find out what I to the 23rd is, we just take that 23 and divide it by 4. How many of these 4s are in there? Because these equal 1. Well, let's see. There's 5, which is 20, and a remainder of 3. This is all I need to know. The remainder of 3 means there's an I to the 3rd left over. After we do all 5 times, we would do I to the 4th 5 times. And that's all 1 times 1 times 1 times. So it doesn't change anything. Equals I to the 3rd. What's I to the 3rd? Negative I. So I to the 23rd equals negative I. Because it's going to keep looping around. I to the 4th is 1. I to the 8th is 1. I to the 12th is 1. I to the 16th is 1. I to the 20th is 1. I to the 21st, 22nd, 23rd. It's going to equal this. So all you need to know is the remainder. When you divide by 4, what's the remainder? And that will tell you where you are in this continuous loop that goes around. So that's how we would simplify I to the 23rd. If you want to know I to the 36th, you divide 36 by 4. Find out it's 9 with a remainder of 0. There's no remainder, so it means it's an even 4. It's just going to equal 1. I to 36 is just going to equal 1 because it's going to equal I to the 4th 9 times. I to the 4th to the 9th. It's just going to be the same as I to the 4th equals 1. You're not going to remember that unless you practice that. So when we get to the practice problems, so here's where it talks about I squared is negative 1. I to the 3rd is negative I, like I just did on paper, and I to the 4th is 1. So here is the repeating. They show this in our lesson. What would I to the 5th simplify to? They show I to the 5th is 5 times i's, which is I squared times I squared, which is negative 1 times negative 1, which is 1, because it's the same as I to the 4th. It's 1 times this leftover I. So it's just I. So there's the first 16. Equals I, negative 1, negative I, 1. Equals I, negative 1, negative 1. Negative 1, negative I, 1. Equals I, negative 1, negative I, 1. And again, the 13th is I, 14th is negative 1, 15th is negative I, 16th is 1. And it will just continue every 4. So that helps simplify. So they did the 27th power. They divided it by 4 to find out 6 times it would loop through there. And then the 7th time, they would get to step 3. So since there's a remainder of 3, it equals negative I. So they did the whole chart there to show you all the way to the 28th. They did it the same way. You would get negative I because it's a remainder of 3. All right, let's look at the next page. This is our last page of lesson, and it has some sample problems for you. All right, so now that we understand not complex numbers, imaginary numbers, let's talk about complex numbers. Imaginary numbers are one piece of a complex number. This is a complex number, 7 plus 10i. So the other part is a real number from that real number box we were looking at earlier. So any complex number, let's put this up like this. Any complex number, A plus BI. A plus BI. That's how we write a complex number. A is real. BI is imaginary. So for example, 5 minus 6i is a complex number. 5 is the real part. Negative 6i is the imaginary part. Okay? Real part, imaginary part. All right, so it has this little walkthrough here. Items will be appended and stored in these categories. So if we have these parts down here, which are the real parts? Which are the imaginary parts? Hint, don't make this harder than it is. It's very simple. Anything that has an I attached to it, negative 6i, is imaginary part of the complex number. 3 is a real part. So 2, is that a real number or imaginary number? Well, 2 is a real number. But 7i is not a real number, so that's the imaginary part. 5 is a real part. I is an imaginary part. 1 is a real part. Negative 10i is an imaginary part. So you put the real parts in the real part, imaginary and imaginary. You dropped them all in the correct category. Yeah, because anything that has an I is the imaginary part, automatically. And you cannot combine those, 3 minus 6i. Because they're two different number systems. The real number system, imaginary number system, you cannot combine those. All right, so here's our lesson summary of what we learned about complex numbers. All right, so I is defined as the square root of negative 1. If you're taking notes for the exam, this is a great place to get them in the lesson summary. I is defined as the square root of negative 1. We can simplify radicals using I. We have the square root of negative 45, which we know does not exist because we cannot take the square root of a negative number. But using imaginary numbers, we can. We break that out into negative 1 times 45. Square root of negative 1 is I, so we write it as I. Square root of 45 can be simplified to the square root of 9 times 5, not times square root of 5. And the square root of 9 is 3, so it's 3i squared to 5. Then it talks about the repeating pattern of I squared, I to the third, and I to the fourth. This is in the lesson summary. And tells what those are equal. And then it repeats constantly. And how would you figure out I to the 27th through this process? So there's a lesson summary going over everything we just looked at in the complex numbers lesson. Now here's the important part. You need to practice. Pages 4 and 5 have practice for you. So here's the first set of practice problems. Right here under the first tab, you try one. Simplify this. What is the square root of negative 64? Well, we know we can pull the square root of negative 1 out, and that would be I, which just leaves the square root of 64. What's the square root of 64? 8. So it would simplify to 8i, because it has that negative 1 and the square root of 64. And we submit that. It says, great job. And then you continue. There's 5 practice problems right there. 5 of them. Now you try the square root of negative 100. So once you get through with these 5 problems, switch over to the second tab. You try 2. Here it asks you I to the 5th. What is that equal to? Is that I, negative 1, negative I, or 1? Well, when you divide that by 4, there's a remainder of 1. So it's going to go in the first category. I squared, we know I squared is negative 1. I to the 7th would have a remainder of 3. It would go in the third one. So continue through those, I to the 20th, to get that done. That's all on this page. Let's look at the next practice problems they give you. The practice problems are great because if you get it wrong, it will tell you what you did wrong. It'll tell you how to do it correctly. All right, here's another one. 5 problems. Simplify this. Here's your choices. 7, negative 7, 7i, or 49i. Well, we know we can break that apart into negative 1. Square root of negative 1 times the square root of 49. Square root of 49 is 7. Square root of negative 1 is I. There you go. And it details it out. It says correct, but then it tells you how you got there. So 5 problems there for your practice. All right. And then that's it for all of the practice problems. So they give you 15 different practice problems, which is great. So you can make sure you understand. If you can't do those practice problems, you need to go back and look at this again. So let's look at the assignment that goes with this first lesson. Oh, I forgot. There's also a video about complex conjugates. And we are going to watch this. It's just a couple of minutes. And here, I need to share this differently, or you won't be able to hear the sound unless I share this differently. This one. This is good because we also use conjugates. Complex numbers have conjugates, and it's very, very simple. So pay attention to this video here.
We're asked to find the conjugate of the complex number 7 minus 5i. And what you're going to find in this video is finding the conjugate of a complex number is shockingly easy. It's really the same as this number. I should say be a little bit more particular. It has the same real part. So the conjugate of this is going to have the exact same real part, but its imaginary part is going to have the opposite sign. So instead of having a negative 5i, it will have a positive 5i. So that right there is the complex conjugate of 7 minus 5i. And sometimes the notation for doing that is you'll take 7 minus 5i. If you have 7 minus 5i, and you put a line over it like that, that means I want the conjugate of 7 minus 5i, and that will equal 7 plus 5i. Or sometimes someone will write, you'll see z is the variable that people often use for complex numbers. If z is 7 minus 5i, if z is 7 minus 5i, then they'll say the complex conjugate of z, and you put that line over the z, is going to be 7 plus 5i. Now you're probably saying, okay, fairly straightforward to find a conjugate of a complex number, but what is it good for? And the simplest reason, or the most basic place where this is useful, is when you multiply any complex number times its conjugate, you're going to get a real number. And I want to emphasize, this right here is the conjugate. 7 plus 5i is the conjugate of 7 minus 5i. But 7 minus 5i is also the conjugate of 7 plus 5i for obvious reasons. If you started with this and you changed the sign of the imaginary part, you would get 7 minus 5i. They're conjugates of each other. But let me show you that when I multiply complex conjugates that I get a real number. So let's multiply 7 minus 5i times 7 plus 5i. And I will do that in blue. 7 minus 5i times 7 plus 5i. And remember, whenever you multiply these expressions, you really just have to multiply every term times each other. You could do the distributive property twice. You could do something like FOIL to remind yourself to multiply every part of this complex number times every part of this complex number. So let's just do it any which way. So you'd have 7 times 7, which is 49. 7 times 5i, which is 35i. Then you have negative 5i times 7, which is negative 35i. You can see the imaginary part is canceling out. Then you have negative 5i times positive 5i. Well, that's negative 25i squared. And negative 25i squared, remember, I squared is negative 1. So negative 25i squared, let me write this down, negative 5i times 5i is negative 25 times I squared. I squared is negative 1. So negative 25 times negative 1 is positive 25. And these two guys over here cancel out, and we're just left with 49 plus 25. See, 50 plus 25 is 75. So this is just 74. So we are just left with the real number 74. Another way to do it, you don't even have to do all this distributive property. You might just recognize that this looks like this is something plus something times, or something minus something times that same something plus something. And we know this pattern from our early algebra, that a plus b times a minus b is equal to a squared minus b squared, is equal to a difference of squares. And so in this case, a is 7, a squared is 49, and b in this case is 5i. B squared is 5i squared, which is 25i squared, which is negative 25. And we're subtracting that. So it's going to be positive plus 25. You add them together, you get 74.
All right. Conjugates. Let me again change how this is presenting so I can show my other screen again. Conjugates. So do not make conjugates difficult. So he explained how to find the conjugate. If we have, let's just make one up, minus 4i This is a complex number because it has a real and imaginary. The conjugate is 2 plus 4i. The only thing that changes is the sign of the imaginary part of the complex number. What if we have 3i? Does that have a conjugate? Yes, this is a complex number. Technically, it would be negative 3i. That would be the complex conjugate. This is the real part is 0. You got 0 plus 3i. So you'd have 0 minus 3i. So 3i has a conjugate of negative 3i. Right. And like you pointed out, when you multiply a number times its conjugate, it becomes a real number. The imaginary part goes away. Goes away. And we'll be using that as we look at simplifying in the next lesson here. So, all right. Now let's look at the assignment that goes with this. Now that we know conjugates. If we start this, first thing it has is simplify the square root of negative 121. Simplify negative 72. Again, that's what we're talking about. You got to be able to rewrite these and break it out. As you see, there's no square root left in that first one because 121 has a square root. Simplify I to the 38th power. Got to know how to use that rule to take that shortcut. Otherwise, you're going to be working this out for a long time, writing out 38 i's there. Simplify 6 plus the square root of negative 80. So notice the 6 plus doesn't change because nothing happens with the 6. You're just simplifying the square root of negative 80. Here's another one down here, I to the 31st power. And then the last one, what is the conjugate of 3 plus 6i? All right. The only thing that changes is the sign. It's 3 minus 6i. Don't make that harder than it is. So, all right, let's look at the next lesson. Like I said, we got a lot throwing at you today. Now we're going to do operations with complex numbers. Since we've learned about complex numbers, let's do complex. So after learning about imaginary numbers, you maybe wonder what purpose they have, because we discovered imaginary numbers and then had to figure out a purpose for them. They're anything but imaginary. So applications of complex numbers can be found in infrastructure, engineers and architects designing suspension bridges, designing airplanes, most notably in the electricity that surrounds you. Calculations of imaginary numbers are used in all of these designs and engineering of all these different things. So we're going to learn how the associative, commutative, and distributive properties can be applied. Combining like terms, if you struggle with that, here's a review, because combining like terms works even with the imaginary numbers. Like when we have 7x squared plus 3x minus 5 plus 2x squared minus 4x plus 9, we can only combine like terms. So they put it in color here. The yellow terms are like terms. They're both x squared terms. 7 plus 2, 9x squared. The green ones are x terms. They're different than x squared terms. You cannot combine them with the x squared terms. But you can combine with each other. You got plus 3x and minus 4x. So that's negative 1. Then the blue is just actual numbers, no variables. Negative 5 plus 9 is plus 4. So there's that simplifies. So the same concept works with complex numbers. So let's put some complex numbers up here real quick and talk about like terms with that. So let's say that we're taking 12 plus 3i. That's a complex number. And with that, we're going to add 10 minus 4i. Taking this complex number and adding it to this one. We can only combine like terms. 12 is a real number. 10 is a real number. Plus 3i and minus 4i are imaginary numbers. So we would combine 12 plus 10 to be 22. And 3i minus 4i would be minus I. Or minus 1i, but we don't put 1 as a coefficient. 22 minus I. That's what that combines to, but you can only combine like terms. If we're subtracting, let's do that. 12 plus 3i minus, I'm going to put in parentheses because I'm subtracting the whole thing. I don't want to mess that up. If I'm subtracting that, what's 12 minus 10? 2. What's 3i? Here's the tricky part. 3i minus negative 4i. 3 minus negative 4. When you subtract a negative, you add. So that equals 2 plus 7i. Because we subtracted a negative. That's why I put it in parentheses. If I didn't put it in parentheses, I might forget that I'm subtracting this, and I might do it wrong like that. Parentheses help a lot. So, all right. Let's see what they have next. Oh, here's where they do the same problem right there, subtracting. So there's a video. If you need a step-by-step on that again, 1 minute, 2 seconds, you can watch them go through the steps. Oh, here's a good one. Let's look at this. I'll write this on paper so we can do this together. So we got 2 plus the square root of 121 plus the square root of negative 9. Oh, that's negative 121. Put a negative in front of that. All right, negative 121. Almost messed that up. All right, so if we're going to add these three terms together, we can't add those. They're not the same. If we have, let's say, if we have 2 square roots of 3 plus 3 square roots of 3, we can actually add those together because they're both square roots of 3. We would have 5 square roots of 3. We can do that. But if this is the square root of 2, we can't do it. They have to be the same square root of 3. These are not the same. We cannot do that. But we can rewrite these. The first thing anytime we have a negative underneath there, we need to rewrite it first. First step. So this is the square root of negative 1 times the square root of 121. Plus the square root of negative 1 times the square root of 9. 1 times 9, negative 1 times 9 is negative 9. Negative 1 times 121 is that. All right, so let's rewrite this again now. 2 plus, what is the square root of 121? That's actually a whole number. This is a perfect square. 11 times 11. And the square root of negative 1 is defined as I. So this is 11i. That's what negative 121 is. The square root of that is 11i. Plus, square root of 9 is 3. And the square root of negative 1 is I. So we got 2 plus 11i plus 3i, which we can simplify to 2 plus 14i. That's our answer. This right here is 2 plus 14i. We got to rewrite that and simplify it before we do the math. And again, they've got a 41-second video this time to where they'll take you through all of the math right there. All right, here's one we have to simplify 4 times the square root. Well, let's do that one because that one's a little differently. 4 times the square root of negative 24 plus square root of negative 150. Again, the only way you're going to get good at this, the only way you're going to understand this is to practice this. So you should get out a pencil and paper, and when they have all these practice problems, you need to work those and practice this. So again, we have to rewrite 4 times the square root of negative 1 times the square root of 24. Those are all multiplied together, right? Plus square root of negative 1 times the square root of 150. Okay, well, we know we have the I. Those become I. But what can we do with this? Can we break this up into something that we can actually pull an integer out of? Well, 24 is 1 times 24. It's 2 times 12. It's 3 times 8. It's 4 times 6. And that's about it. So are any of those perfect squares? Oh, yes, look at there. So let's rewrite that. Let's go ahead and make this an I. So this is 4I times, we're going to rewrite this as the square root of 4 times the square root of 6. Because 4 times 6 is 24. And over here, 150, see, 1 times 150, 2 times 75, 3 times 50, 4 doesn't work, 5 times 30, 6 times 25, maybe about it. Oh, no, 10 times 15. Are any of these perfect squares? Oh, looky there. 25. We can take the square root of 25. So let's rewrite this as I, the square root of -1, that's an I. And then we have the square root of 25 times the square root of 6. 25 and 6 is 150. So now I've rewritten those. I can take the square root of 4, and I can take the square root of 25. So now I've got 4I times 2, because that's the square root of 4, times the square root of 6. And over here I have I times 5 times the square root of 6. So 4I times 2 is 8I square roots of 6. That's as simplified as the square root it gets. We can't do anything with the 6. Plus 5I square roots of 6. Oh, look, this principle is going to come into play. These are both square roots of 6, and they're both imaginary numbers. So this is 13I square roots of 6. That's what this number plus this number is 13I square roots of 6. Got to simplify and walk through the steps, and they will have you factor it, simplify it, and combine it at the end to be 13I square roots of 6. So they walk through the same steps right there that I just did on paper. Let's go to the next page. This page is the last page of this lesson, because when we scroll down, we see the lesson summaries at the bottom. So 2 pages. Lesson summary for your notes. Let's see what they're telling us on this page. Multiplying complex numbers. Okay, so we need to be able to multiply complex numbers. And it's very important that we do that correctly. So let's look at square root of negative 12 times the square root of -5. Now, the important part about this is when we're multiplying radicals, a lot of times we want to do the multiplication first. That's going to create a problem. Because if we do the multiplication first, -12 times -5, we're going to say, oh, square root is square root of 60. The imaginary part went away already. There's no imaginary. That square root of 60 is a number. But we can't do that. We have to rewrite first. This is the square root of -1 times the square root of 12 times the square root of -1 times the square root of 5. These are all being multiplied together. So the square root of -1 times the square root of -1. Like we got both of those in there. So the square root of -1 times the square root of -1 is just -1 times 12. We see 12 is 1 and 12, 2 and 6, 3 and 4. So let's rewrite that as the square root of 4 times the square root of 3. And then we still have the square root of 5 being multiplied by that too. We took the 2 square roots of -1, and that is -1. The square root of 4 is 2 times 2 times the square root of 3 times the square root of 5. So this is -2, and then we can go ahead and combine these because that's as simple as it gets. -2 square roots of 15. If we had done this first, which this is a mistake, don't do this. 60 is 4 times 15, so we could have rewritten that. The square root of 4 times the square root of 15, and we would have come up with 2 square roots of 15. But that's wrong, right? Because you lost this part. You lost the negative. Do not multiply these together first. You need to rewrite them first. Pull out the -1. Square root of -1 times square root of -1. So don't make that mistake of jumping the gun and multiplying them together until you've rewritten to pull out the I values. I. So this is I squared, which is -1. So they will go over that. I squared 60, all of that. They do show how to pull out the prime factors. If you don't know the factors of 60, you can say, well, there's a 2 times 30, which is 3 times 10, which is 2 times 5. So the factors are 2, 3, 2, and 5. And since I have 2 2's underneath the square root, that's 4. It comes outside as a 2. 2I squared square root of 15. And different way of factoring that. But there's the final answer. -2 square roots of 15 that we got through working that on paper there. Here's what it talks about. What would have happened if you'd multiplied the radicands first? Then you end up with that mistake of 2 square roots of 15 and you lost the negative. So you're wrong because you missed that negative. So the imaginary number must be factored first. All right, here's another video. It's 56 seconds. Let's work this one on paper. Get out another sheet here. There, I'll work on the back of this one. Okay. Let me write this down. The square root of -3 times 12 plus the square root of -6. Okay. And again, there's another video. If you don't understand how I do it, you can see how they do it on their video. Maybe that'll help make more sense. Let's see. We have to distribute, right? Distribute because we have a -3 times what's in parentheses. A square root of -3. So square root of -3 times 12 is just 12 square roots of -3. There's nothing we can combine there. Square root of -3 times the square root of -6. Oh, we may run into one of those problems again where that would become a positive and put us in the wrong direction. Because if we just did that, we would say that is the square root of 18, which would simplify to the square root of 9 times the square root of 2. So that would be 3 square roots of 2. So in this way, we end up with 12 square roots of -3, which would be, pull out the square root of -1, 12I square roots of 3 plus 3 square roots of 2. But what happens if we rewrite these first? Square root of -3 would be I square roots of 3 times 12 plus I square roots of 6, right? Because we broke that out as a square root of -1 and square root of -6. I'm sorry, square root of -1 times square root of 6, which is I square roots of 6. Now when we combine these, I square roots of 3 times 12 is 12I square roots of 3. Look there, nothing changed on that. That's the same thing we got here. What about when we multiply these together? Now we get I times I is I squared square roots of 18. Well, square root of 18 is still going to break out the same way. It's going to be 3 square roots of 2. And this is 3. I'm not writing very good today here. But what's I squared? I squared equals -1. So this is negative. See, if we don't break out and simplify the I term, this ends up backwards. Instead of positive, it should be a negative. Let's see what their video says about that. See, they break out the negative ones first. That's got to be the first step. So at the end, you end up, they showed the mistake on that too. So that's the I squared plus I squared, 3I squared, -1. There's the -3. And for some reason, see, that's the correct answer. They're putting them in order of the smaller square root first. This is the same answer. 12I square roots of 3 minus 3 square roots of 2 is the same as minus 3 square roots of 2 plus 12I. They just like to write this. I don't care if you leave it like this, that's fine. Square roots of 3 first and then negative second. But again, if you do that in the wrong order. All right, we're going to look at, there's another example if you need to look at that. I'm going to look at, that's a distributive property. Now we probably have to look at that together too. I was going to skip that one, but we need to look at the distributive property.
Hi, Kara.
And this, they already put it as i's. Put it as i's. So let's go through the distributive property. So if you have 6 minus 3i times 5 plus 9i. Remember, distributing, you got to multiply the first term times both terms. Then we do the same thing with the second term. So the first term, 6 times 5, and then 6 times 9i, the positive 54i. Then we take the second term and we multiply it. Negative 3i times 5 is negative 15i. And then negative 3i times 9i. Negative 3 times 9 is negative 27. I times I is I squared. Well, this negative 27i squared, since I squared is -1, this is negative 27 times -1. So this simplifies to a plus 27. We got 30 front. These are like terms. They're both i's. So 54 minus 15 would be plus 39i. But we still have two real parts. 30 plus 27. So the answer is 57 plus 39i. 57 plus 39i. Just because we combined the 30 and 27. Let's talk about the conjugates again real quick, and then multiplying a complex number by its conjugate. All right, so this will be the last thing we need to cover here for this lesson. And we're just going to make up our own number here. So we're going to say we have a complex number, 7 minus 3i. Okay, that's our complex number, right? It's got a real part, it's got an imaginary part. The conjugate, if we're going to multiply it by its conjugate, is 7 plus 3i, right? Remember, it's exactly the same numbers, you just changed the sign. So that's the conjugate. And if we multiply a number by its conjugate, it's important to pay attention to. When you get this, when you have something multiplied by its conjugate, it will be a real number. Every time. When you multiply a complex number by its conjugate, it will no longer be imaginary. These are both imaginary numbers, but it will be a real answer. So let's work that out. Just like above, we have to distribute. So 7 times 7, 49. 7 times 3i, 21i. Negative 3i times 7, negative 21i. Negative 3i times positive 3i, negative 9i squared. And again, just like up here, if you got I squared, that's negative 9 times negative 1, because that's what I squared equals. So this becomes plus 9. So this is 49, 21i minus 21i. And this is, we said, was plus 9. So 49 plus 9, 58. Multiplying these two imaginary numbers gives us a real answer. 58, that's a real number. But these are conjugates.
timer on here in just a minute.
And when you multiply conjugates, you get a real answer. When you multiply conjugates, you get a real answer. That's important to remember. Because if you don't end up with a real number, if there's an I in your answer, you've messed something up. When multiplying conjugates only. That's the only time I'm talking about this. Because when we multiplied these were not conjugates of each other, and we ended up with an imaginary answer. It's only when they're conjugates do we know for sure we should have a real solution. So, again, there are 2 pages of practice problems to help you make sure you understand what we're doing. Here's the first ones. This again has 2 tabs. You try 1, you try 2. Simplify according to the given directions. And this one, you're adding them. You got to add 12 minus 3i plus 9 plus 2i. You add the real parts, you add the imaginary parts. Okay, it's got 5 of those. Then you switch over here. Simplify these and match the answers. Square root of -3 times 7. What does that simplify to? It's like, ooh, wow, none of those even have a 7 in them. There's one with a 3, but somehow that simplifies. Right? Because you pull out the I, so then you got the square root of 3 times square root of 7. So it's gonna go right there. I square roots of 21. So the next page of practice problems. You should do these on paper. Correctly simplify each of the following expressions involving complex numbers. 6 questions right here. Simplify this plus this. Pull out the I value. Simplify the square root of 50 and the square root of 72. Figure out which one of these it ends up with. Submit and see if you're correct. If you just take a guess, is it that one? Oh, I hit submit. It didn't get it. Nope. Try again. That's not the answer. Recall that I equals the square root of number 1. Factor the perfect squares. I knew that wasn't right. So, all right, 6 practice problems there. All right, let's go look at the assignment that goes with this. Multiple choice. Simplify the given expression. 3 plus 4i plus 5 minus 2i. Which one of those will it equal? Here's 2 more complex numbers being subtracted this time. If you subtract this complex number from that, which one of these do you get? Simplify this. Multiplying 2 complex numbers. Again, multiplying. And the last one is multiplying. But look, those are conjugates. 6 plus 2i and 6 minus 2i are conjugates. That tells you it should be a real answer. You can already rule out the last 2 because those have imaginary solutions. If you're multiplying conjugates, it should be either 32 or 40. So there you go. That's it. We had a lot today. There's a lot to it. I'll be editing the video and posting that to Google Classroom whenever that gets done. That's going to take a little while. It's a long video. It takes a long time to process and give it to me. So, all right. Any questions? We're right in the middle of this unit. We got 2 more weeks till we test. We've been in it for a couple of weeks. We're good. All right, guys, I'll let you go enjoy it. This is a B-Day Friday. So if your grade's below 70, either get your grade above 70 or I'll see you Thursday and Friday. So, all right. Have a great week.